Our next speaker is Dr. Ratul Chowdhury, who is an assistant professor and Building a World of Difference faculty fellow, that's a mouthful, in the Department of Chemical and Biological Engineering at Iowa State University. His research focuses on computational protein design, protein dynamics, and structure-guided metabolic engineering. He is leading the Finding NEMO project, which employs AI-driven structural computational biology to identify novel inhibitors of the MCR enzyme, aiming to reduce enteric methane emissions in livestock. Welcome.
Thanks for the welcome. Really happy to be here. Okay, sorry, this way. Yep, so I am Ratul, I'm from Iowa State. We look at computational structural biology and also use some data-driven modeling. So the relevance of this in this session is that the genesis of methane in livestock is from an enzyme. So this is conserved across all strains of methanogenic bacteria that you might find in different ecotypes of the rumen of different cows. So one thing that's consistent is that there is an enzyme that produces that methane. And there are other steps which also involve enzymes. For example, if you were to look at some feed additives involving tannins, and sometimes you see that these molecules are pretty big. And if you have to pre-process them and get them to their right size so that they're a bit more effective, you might consider enzymatic pre-processing of these feed additives. And finally, there is also some talks about vaccines. So when you have a vaccine for the bacteria, there is a chance that the bacteria also evolves out of the antibodies that you design. And we have seen that happen with SARS-CoV-2. We've taken 4 vaccination shots in a matter of 4 years. So to stay ahead of the curve, we need to understand some amount of structural biology. This is where we are getting at. One thing I would say is that we design different types of enzymes, and enzyme engineering has been done over more than a decade now, computationally at least. So what we bring onto the table slightly differently is that when you look at a traditional enzyme engineering pipeline, it suggests point mutations or changes to that enzyme that can drive towards a certain functionality. And all the classical tools that are out there that suggests amino acid changes, not deletions or insertions. But when you look at a multiple sequence alignment of like a family of enzymes in nature, which all perform the same task, you'll see these dashes in a sequence alignment, which means that nature uses different sizes proteins to do the same task often. So we try to incorporate that as an option when we are trying to build new enzymes. And that is, you can see, even for a very conserved family of enzymes like TM1 beta lactamases, if you do not allow for the size to change, you will actually miss 62% of the family members that could be sampled. So we have this pipeline which allows for enzyme engineering for different tasks where we can now make an insertion or a deletion and target it towards a specific objective. And next question is that now we're looking at trying to map structure to function. So the first question is, when you're looking at an enzyme, how much of the structure is relevant? So because the catalytic activity, so for example, if methane is produced by an enzyme, the core location, the groove where the activity happens is a very small location. So if you were to just focus on that tiny small location, you're going to miss the activity pretty big time because there are surrounding locations which actually support that activity. But if you take the whole enzyme, then you're again going to have a lot of information which will be noise and not really signal. So there is a question as to how much of the structure should we actually look at to understand the function. To this end, we've been looking at the more popular class of enzymes called hydrolases, and we've created a database of 40,000 hydrolases to understand how much of the structure is relevant. And utility of the structure-based design is kind of important because oftentimes, let's say, for industrial processes, when you are making a specific molecule, this could be your feed additive molecule, you have impurities which could come in the form of sugars or trace DNA. If you want to cut out those extra molecules, you have to use enzymatic steps. And it often comes down to the fact that what is the cascade of these enzymatic steps to cut these extra impurities out. So we are driving towards a point where we can say that we can pack multiple activities in one enzyme and call it like a multifunctional enzyme. So there is this database that we put together, which is now currently present in the protein data bank, publicly live. You can functionally classify enzymes based on the structural similarity that they have. And finally, coming to, in the protein structure world, you have heard of AlphaFold getting the Nobel Prize last year. We say that for this enteric methanogenesis type projects, AlphaFold is not necessarily the best bet, because if you make small mutations and your protein becomes slightly different from the homologous protein set, so if the enzyme needs to mutate or the bacteria needs to mutate in a certain way, if your homology drops below a certain level, the AlphaFold prediction takes a nosedive. That's primarily because the way it's set up. I can talk about that in detail when we meet, but specifically to that end, we built a process which can understand protein design and understand how to predict structures from single sequences. And then finally, protein function is we want to understand how to predict enzyme activity. For example, the methanogenesis enzyme, MCR enzyme, if you have to predict the activity, how do we make a data-driven process for predicting activity? There's a couple of tools out there which predict activity and claim state-of-the-art, but they all fail in some common thing, is that they try to predict the exact value of the activity. And I think that's largely missing the point, because activity ranges 16 orders of magnitude, and you cannot necessarily pinpoint it. So what we've shown is that we can bucket it up, saying that what order of magnitude is your activity on, and if you can predict that, that is a more easier and a reasonable task. And finally, we've done this work in terms of predicting activity of enzymes, and this is currently under review. And finally, we also show this thing that if you take an enzyme and mutate its catalytic residue, the catalytic apparatus is missing, let's say, all the current tools will tell you that it's a small change, so your enzyme is still functional. But in reality, what it means, if your enzyme is missing the catalytic groove, you are going to get a zero catalytic rate. And this is what we have been trying to target. It took us like 12 months of work to get to a model to understand what is catalysis. And this is what we are implementing on a different industrial enzymes, and for which we have data sets, and we are now getting very strong correlations with industrial data. And this is finally looking at transferring all this knowledge to the MCR enzyme, which is a beast in itself, because this enzyme has a F430 cofactor, which is a moving piece within the enzyme, and there's a nickel, which is another moving piece within the F430, and then you have a substrate that's coming in, which you want to inhibit with your inhibitor molecule. So we are trying to build all of these facilities up and try to understand how to design better inhibitors. And finally, we've done some preliminary work in scoping out the mechanism of all the 16 known anti-methanogenic molecules so far reported in literature, and using this as a prior to our machine learning model to design better molecules. Finally, I leave this with this final slide. We are building contrastive machine learning models, which is trying to distinguish our molecules from 3-NOP so that we can also foray into new intellectual property space. Thank you.